Hello, good evening. Am I audible to you? Nirmal.
Yes, sir.
Yeah, thank you. So we'll start the class now. Uh, my name is Ranjan Bora and I am a PhD scholar at the Mechanical Engineering Department in IIT Delhi. And I am one of the TA in this course, Biomechanics of Joints and Orthopaedic Implants. This course is instructed by Professor Sanjay Gupta. And I have already taken 3 lectures for the past 3 weeks and uploaded those lectures in my YouTube channel. So if you have missed those lectures, you can go through that and you will find the link to those videos from the NPTEL website. And today is the week 4 tutorial. So today, first I will solve the assignment from week 3, and then I will I will explain some concepts from week 4, like moments of inertia and how to use the moments of inertia to solve the numerical problems for calculation of moment about a joint. And I will solve some numerical problems also. So yeah, first I will solve the assignment from week 3. So I think you have already submitted. So let's start. So this was the first question. Is the distance between corresponding successive instance of heel contact of one foot with that of the other foot. So Nirmal, did you submit the assignment for last week 3?
Yes, sir.
Yeah, so I think you know the answer. What is the answer for this question? What is the correct option? Okay, so the answer is the step length. So you can see this is a gauge cycle, and here it is asking in the corresponding successive instance of heel contact of one foot with that of the other foot. So means this is the right foot and this is the left foot. Then this distance is the step length. So option B is correct. And the next question is about the distance between successive instance of heel contact of the same foot. So the distance between the heel contact of the same foot is the stride length. This is the stride length. Okay. Next question is swing phase constitute percentage of the gauge cycle. So how much percentage of the gauge cycle does the swing phase constitute? So it is 40%. You can see this is the gauge cycle for the left foot, and for the left foot, first phase is the swing phase, which constitute 40%, and the next phase is the stance phase, which constitutes 60%. So swing phase constitute 40% of the gauge cycle. And next question is what happens to the time duration of swing phase when the walking speed increases? So if the working speed increases, then you can see the time duration is shown here. Time duration of stance phase decreases, swing phase increases, and double support phase decreases. So it is asking the time duration of swing phase. So time duration of swing phase increases. Option A is correct. And the next question is, the human gait has dash determinants to minimize energy expenditure. How many determinants have? So these are the determinants. Like one is compass gait, then pelvic rotation, pelvic tilt, lateral displacement, stance knee flexion, and dorsiflexion and plantar flexion. So total it has six determinants to minimize the energy expenditure. Next question is, the purpose of locomotion is to transport the body over a distance with disturbance to the center of mass. So option A is correct. Like the purpose of our locomotion is to carry our body with the minimum consumption of energy. So means minimum disturbance means the consumption of energy is minimum. So that's why option A is correct. And the vector of the ground reaction force in a healthy body should test the body. So you can see this pink color line is the ground reaction force of a normal person, and it passes through the body. And um, means for a patient with gait disorder, the ground reaction force passes outside the body, and it increases the momentum. Okay, so option A is correct. Next question is, in the Trendelenburg gait, the pelvis tilts dash on the non-weight bearing extremity. So it is a kind of gait disorder. And in this type of gait disorder, the pelvis tilts downwards instead of upwards. You can see this is for a normal gait where this uh, pelvis is means in the horizontal plane. And for the case of Trendelenburg gait, the uh, pelvis tilts towards the left side. You can see pelvis drop, and the weak gluteus medius uh, weak gluteus medius muscles. This is the weak gluteus medius muscles, and means there is an there is a rise in this side and drop in the left side. So option A is right, correct. The pelvis tilts downwards instead of upwards. Next question is, and dash is an electronic device that measures and reports a body's specific force, angular rate, and sometimes the orientation of the body. What is the answer? So option A is right, correct, that this inertial measurement unit, this is a kind of device which is used for measuring the specific force, means by by placing the device on the ankle, we can measure the accelerations of the ankle and the angular rate and sometimes the orientation also. So these are the parameters we can measure using an IMU. And next question is the gait abnormality where the stand space is abnormally shortened in comparison to the swing phase. So this is an example of antalgic gait. And in antalgic gait, what happens because of the osteoarthritis, there are some pain in the hips, pain in the knee joint. So to compensate the pain, what the person do, the person means the stand space shorten in comparison to the swing phase. So while the person walks, then he or she tends to place his foot, means he takes lesser time in the stand space and he takes more time for the swing phase uh, for getting some comfort from the pain. So, and the common causes for antalgic gait is osteoarthritis, rheumatoid arthritis, and tendinitis. So these are some disease which happens in our joints. So this is a image for osteoarthritis, and this is a image for rheumatoid arthritis. Okay, next question is gait measurement with the sensors is dependent on the research laboratory. So you have studied in the week 3 slides that the gait measurement we can do using two systems. One is the wearable systems and another one is the non-wearable systems. So you can see the image. This is an example of wearable systems. Means all the measurement devices the subject can wear on his body, and it is an example of non-wearable system. Means the devices are not on the body. They are placed means in a laboratory. So you can see like here number 3 is some force plate. Then and this one are the cameras to capture the coordinates of the markers, and here are the systems. So in the case of non-wearable systems, we require a research laboratory. So here option A is correct. And next question is traditional gait analysis involves dash measurement. What is the answer? Traditional gait analysis. So it involves the subjective measurement. We need some subjects to measure the gait in a laboratory. So option B is correct. And next question is electromyography is a technique for evaluating and recording the electrical activity produced by skeletal muscles. So is it a true or false? So you can see this figure. This is an EMG device which we place on our skin. Means below the skin there are muscles. So using this device we can record the electrical activity of our muscles. Means on which muscle this sensor is placed. So it will measure the electrical activity for that muscle. So it is a true statement. And the next question is, the HIP 98 is a database of hip contact forces and gait data during various daily activities. So what is a HIP 98 database? Like the HIP 98 database was developed by Bergman et al. And Hiller et al. In the year 2001. And it is a comprehensive data set on musculoskeletal forces in the hip joint. And what did they do? They used their hip implant, and they used some instruments here, inserted the instrument inside the hip implant, and they implanted this implant in some subject, and they performed different activities for those subjects, and they measured the reaction forces on the hip joint during those different activities, and they have reported it, and they have prepared a database that is known as the HIP 90 database. So it is a true statement. And the next question is, in a single-legged stance, the effective center of gravity moves distally and away from so in a single leg stance, the effective center of gravity moves distally and away from the supporting leg to maintain the balance of the body. So option A is correct. And next is, which is a correct statement regarding stance space? The stance space begins at heel strike. So you can see this is the stance space for the right foot, and when it starts at the right in contact of the heel. So it begins at the heel strike. And what about the swing phase? The swing phase starts here, and it begins at uh, when the toes gets off from the ground. So option A, begins at toe off. And next question is, how many transformation matrices are required between marker coordinate system and global coordinate system? So you can see this is the global coordinate system, and when we place the marker uh, on the on the body part, then it creates one coordinate system of its own. So this is the marker coordinate system. And what is the question? The question is asking how many transformation matrices are required, marker coordinate system and global coordinate system. Means for finding out the for measuring the movement of this body part. So one transformation we require is from global coordinate system to marker coordinate system, and the second transformation we need, that is from the marker to the anatomical coordinate system. So we require two transformations. Next question is, the double support phase constitute approximately what percentage of gauge cycle? So you can see here, first phase is the double support phase. It consists of 10%, and the last phase of the stance phase is also a double support phase, and it also consists of 10%. So total it consists of 20% of the gauge cycle. And the next question is, by reducing the lateral displacement of center of gravity is reduced. Okay, so you can see uh, by reducing this working base, when we reduce the working base, then the distance between the 2 foot will become minimum, means it will become shorter. So the lateral displacement, the displacement along this direction will be reduced. So option A is correct. Okay, so that was all about the assignment from the last week. So now I will explain some concepts from week 4, and then I will solve some numerical problems related to those concepts. So if you have any question, you can ask. Okay, I'll start with equations of motion. So in the last week, I have solved some numerical problems for finding the joint reaction force. Joint reaction force using different method, like force equilibrium method, and then vector force method, and the Lami's theorem. And today I will explain about the Newton's second law of motion, and then and after that I will explain about moment of inertia, and I will solve some problems using these two concepts. So first one is the Newton's second law of motion. What is the Newton's second law? So the Newton's second law of motion states that an object's acceleration is directly proportional to the net force acting on the object. So and using the equation, we can write like summation fx equal to mass into acceleration of the center of gravity in the x direction, and summation fy equal to mass into acceleration of center of gravity in the y direction. So these are for these two equations are for linear system, means when there is no rotation, only for translation. For translation, we can use these two equations. And when there is rotational system. So when there is rotation, then there will be some angular acceleration and there will be a moment of inertia. So using this equation, summation of moment equal to moment of inertia multiplied by the angular acceleration. So we can find out the moment about any joint. Now this moment of inertia, I will explain what is this moment of inertia. So in this course, we will use this mass moment of inertia. So there are two types of moment of inertia. One is the area moment of inertia and another one is the mass moment of inertia. So for solving the dynamics problems, we will need this mass moment of inertia. So what is this mass moment of inertia? Like you can see there is an object of mass m. Now if we divide this object into n number of small objects such that each small object has a mass m1 and the distance from each small object center of gravity to the, if we consider this is the axis of rotation. So the distance between the axis of rotation and the center of gravity of each small object is represented by x. Then we can write the moment of inertia for this whole body will be the summation of moment of inertia of for each small body. So what is the moment of inertia for the small body of mass m1? It is m1 multiplied by x1 square. So what is the x1? X1 is the distance between the axis of rotation and the center of gravity of that mass. So like that, for the mass m2, the moment of inertia is m2 multiplied by x2 square. You can see this is the x2. And if we do the summation of moment of inertia for all the small masses, like this is the nth mass, which is which moment of inertia is given by mn into xn square, we get this. The moment of inertia for the whole mass is summation of I equal to 1 tends to n into mi multiplied by xi square. So this is the formula to calculate the moment of inertia for a mass m. Now there is one theorem in the for calculation of the moment of inertia, which is called parallel axis theorem. Like if this is the mass m, this is the mass m, and this is its center of gravity cz. So the moment of inertia about its center of gravity is I naught. Now if we want to know the moment of inertia of this mass m about this point, which is colored as green. So and if this distance from this green colored point to the center of gravity is x, then using the parallel axis theorem we can write the moment of inertia about this point x is equal to I equal to I naught is the moment of inertia about its center of gravity plus m multiplied by distance whole square. So this is the formula for parallel axis theorem for calculating the moment of inertia about any axis which is at a distance of x from its center of gravity. So here I naught is the moment of inertia about center of mass or center of gravity, and x is the distance between center of mass and center of rotation, and m is the mass of the segment. Okay, so using that concept, now I will solve one problem. Like first, in this problem, first we need to find out the moment of inertia using that parallel axis theorem, and then after that, I will use the moment of inertia to solve to find out the moment m naught about the knee joint. So the question you can read here. We need to find the magnitude and direction of the moment m naught that must be generated by the knee muscles to produce a tangential acceleration of 20 meter per second square at the ankle in the figure shown, and the moment of inertia of the lower leg and foot about the center of gravity is given 0.06 kg meter square and 0.02. So moment of inertia of this is the lower leg and this is the foot. So moment of inertia for these two bodies are given. Now the center of gravity of lower leg and foot are located. So the distance of the center of gravity from the axis of rotation are also given. So how we will solve this problem? Okay, so here center of gravity of the lower leg is here and the center of gravity of foot is here. So this is lower leg and this is foot. So first we need to find this distance. So for the lower leg, so here it is given 20 centimeter along x-axis. So this is 0.2. I'm writing it in SI unit, and at 2 centimeter along y-axis. So it will be 0.02. So what is this distance? That this be d. So d will be equal to, we need to use the Pythagoras theorem, 0.2 whole square plus, so it will be almost 0.2 only. Okay, so we have got d. Now we need to find the distance for this ankle also. So means the for the foot, it will be, for the foot this distance is 50 centimeters, so it is 0.5, and along y-axis it is 0.05, and this, let it be d1, it is d2. So what is d2? It will be 0.5 square plus 0.05 square. This was for CG of lower leg, and this is for CG of foot. It will be 0.502. Okay, its unit is meter. So we have got d1 and d2. Now we'll calculate the moment of inertia moment of inertia of the lower leg and foot about this axis. About D means about the knee joint. So about the knee joint. I is equal to, this is for lower leg. So it is moment of inertia about its center of gravity plus mass of lower leg multiplied by for the lower leg. This distance was d1 multiplied by d1 square. So it will be moment of inertia is given 0.06, 0.06 plus mass. Mass is given 3.537 kg. 3.537 dot d1 we got 0.2. So it is it is 0.2 kg meter square. Okay, and for the foot, it is I naught of foot plus mass of foot multiplied by d2 square. So moment of inertia of the foot about the center of gravity is 0.02 plus mass of the foot is 1.11 multiplied by 0.502. It is coming 0.29 kg meter square. So we have found moment of inertia of the lower leg and the foot with respect to the knee joint. Okay, so what will be the total moment of inertia about the knee joint? The total moment of inertia will be I equal to ILL plus IF. It will be 0.49 kg meter square. So we have found the moment of inertia. Now what we need to calculate? We need to calculate the magnitude and direction of moment m naught. So m naught is shown here in the picture, like in the anti-clockwise direction. So which formula we'll use now? Now we'll use this formula. This one, the summation of m naught, summation of m equal to I multiplied by alpha. So is alpha is given? Yes. Like you can see the tangential acceleration is given. So now we need to find out the angular acceleration using this tangential acceleration. So there is one relation which is omega, sorry, not this one. So there is this a t equal to r dot alpha. Okay, tangential acceleration is given by r is means r is this distance from the knee joint to the means the perpendicular distance between the knee joint and the direction of the tangential acceleration is denoted by r. So this expression will be used for finding the alpha. So what will be the alpha? Alpha equal to AT divided by R. So what is AT is given 20. And this distance is given. This is 50 centimeter. So this is 0.5 meter. So it will be 40. 40 radian per second square. So we have got alpha. Sorry, we have got alpha. Now we will use that equation summation m equal to I dot alpha. So what will be the summation m? So we'll take this direction as positive, means anti-clockwise direction is positive. So m naught is given in the anti-clockwise direction. So we'll write m naught. Then one moment will be because of this W1, and it will produce moment in the clockwise direction. So it will be, what is W1? W1 we need to find out from this weight, like 3.537 kg. So we need to multiply with the acceleration due to gravity. So it is m naught minus W1 dot this distance is 0.2 and minus W2 dot 0.5, because W2 will also produce moment in the clockwise direction. And this will be equal to I dot alpha. So now m naught minus, what is W1? W1 is 3.537 into 9.8 into 0.2 minus 1.11, 9.8, 0.5 equal to I is 0.49 and alpha is 40. So if we solve this, then we'll get m naught equal to so m naught is 31.97. And what is the unit of moment? It is Newton meter. So this much of moment need to be produced by the knee muscles for getting this angular acceleration of 40 radian per second square. I hope it is clear to you. Okay, next, one more concept from week 4 is the joint kinematics. So what is the joint kinematics means? Using the joint kinematics, we can measure the velocity acceleration of any joint for any subject means during its motion. So there are two methods, like you can see for calculating the linear velocity, we can use the central difference approximation, and the method for this central difference approximation is formula is given here. Vxi equal to xi plus 1 minus xi minus 1 divided by total time duration for those two steps. And similarly, the linear acceleration at the ith time instance is given by Vxi plus 1 minus Vxi minus 1 divided by twice of delta t. So we can use these two formulas for finding the velocity and acceleration for any joint. So there is one problem now, so we'll solve this problem. So this problem, here it is asking, from the coordinate data, calculate the acceleration of the knee in the x direction for frame 3. So in this figure, you can see a person is walking along the x direction. And here are some data which are given for different time instance, like the coordinate, like the position of the knee joint for different time steps. So, and it is asking the acceleration for the frame 3, that is this frame. So what is the acceleration for this frame will be? Acceleration for frame 3 will be, see, this was the formula, Vxi plus 1 minus Vxi minus 1 divided by twice delta t. So this acceleration will be V of means 3 to 4 minus P of 2 to 3 divided by total time. How much is the total time? It is delta t for 3 to 4 plus delta t for 2 to 3. So now again, we don't know this v velocity. So first we need to find out the velocity. So what is the velocity for 3 to 4? Means for frame 3, from frame 3 to frame 4, it will be x position position for frame 4 minus position for frame 3 divided by the time step. So this was the formula. Okay, sorry, this will not be x4 minus x3. So this will be, let me write. So this is 4 minus 2. So now V4 is x5 minus x3, and the delta t for 3 to 4 plus delta t for 4 to 5. So if we substitute these values here, x5, what is x5? It is 0 0.5613 minus, and x3 is 0 0.485 divided by delta t for 3 to 4 3 to 4 will be this T4 minus T3 plus T5 minus T4. So here T4 will be cancelled out. So it will be, if we substitute here, T5 is 0.057 and T3 is 0.029. So if we do this, it will be so it is 2.725 meter per second. If we substitute T3 and T5, we will get this value, V4. So similarly, we will find out V2. V2 will be x3 minus x1 divided by delta T of one to two plus delta T of 2 to 3. So if we, what is x3? 0.485, 0.485 minus x1 is this one, 0.4075, and delta T1 to 2, we can write T2 minus T1 plus T3 minus T2. So T2 cancel out. So here, if we substitute T3 and T1, what do we get? What is T3? 0.029 minus T1 is 0. So we'll get 2.672 meter per second. So we have got V2 and V4. Now we can use this equation for finding the acceleration for the frame 3. So using that equation, V4 minus V2 divided by delta T 2 to 3 plus 3 to 4. If we do the simplification, then T2, this is T3 minus T2 plus T4 minus T3. So T3, T3 gets cancelled. Now if we substitute here, V4 was 2.725 minus 2.672 and T4 is 0.043 minus T2 is 0.014. 2.725 minus 2.2. So it is coming 1.827. And what will be the unit for acceleration? It is meter per second square. Okay, this is acceleration for frame 3. So is it clear? Nirmal Kumar, are you attending?
Yes, sir.
Yeah. So have you understood this problem?
Yes, sir.
Okay, that's good. So if you can't understand anything, you can ask me. Okay, next concept from week 4 is the musculoskeletal model. So what is a musculoskeletal model? Like from this figure, you can see this is a musculoskeletal model and why we need this model. So we use this model means for calculating the joint reaction force using the simulation. So means whatever we have learned till now, like the using hand calculation, we can calculate the joint reaction force. But for complex scenarios and for some complex joint, there is one alternative for the hand calculation, and that is the using some software simulation. So to perform the software simulation, we need some musculoskeletal model, and we can use this model for calculation of different joint injection force for different activities. So this musculoskeletal model consists of some basic parts, which are means the rigid bodies. Like what are the rigid bodies? Rigid bodies means the bones which are present in our body. Like you can see the skull, then torso, then femur, tibia. All these bodies are all these bodies are represented as rigid bodies, and we measure their mass, moment of inertia, and then we use those inertial properties in our model. And how we connect these rigid bodies? So like we know that between the femur and tibia there is this knee joint. So we connect the femur bone and tibia bone using the knee joint, and uh, and we specify the like whatever the degrees of freedom for that joint. Like knee joint is a 6 degree of freedom joint. So in our model also we specify that numbers of degrees of freedom. For the hip joint, we use the 3 degrees of freedom. So like that, we can model the whole body using some rigid bodies and joints and actuators. What are the actuators? Actuators are these muscles. These red colored ones are these are the muscles. So here you can see the muscles are represented using a single line. So the whole muscle volume we represent using a single line in a musculoskeletal model. And similar to these inertial properties, we also need some muscle properties also, like what is the maximum force that muscle can generate, and what is the pennation angle, optimal fiber length, tendon slack length. Those parameters we need for developing the musculoskeletal model. So next, there are some method like for calculating these joint force and moments. You can see this flow chart. Like we have solved some problems to calculate the joint force and moments using the equations of motion, which today I explained the equations of motion. That means Newton's second law of Newton. So in the software also we can do the same kind of problem. Like for that we need this anthropometric data, which means we need the masses, lengths, and moment of inertia, and we need the ground reaction force data, and we need the marker position data from the motion capture system. Like for different activities, this marker position data will be different. Like for example, while walking, the marker will move in a means the marker coordinates will represent the activity of a walking. Now, while doing another activity like squatting or lifting weight, uh, so we'll record those activity by placing the markers on this subject, and then using the cameras, and you have which you have means which was explained in the last week content. So you can see like the measurement system, how we can measure the data. We can measure the data in the gate lab by placing markers and using different sensors. So those data, from those data, we get these velocities and accelerations. Like one example today I have shown how to calculate the velocity and acceleration using the position data and the time data. So all the hand calculations we have performed in this course till now. So those calculations we can do using the softwares. So for doing those calculations, we need to provide some input, and these are the inputs which are here shown in the circle, doing the circle. Like anthropometric data we need, and we need the marker position data, and we need the force data. So if we get these three data, then we don't need to do the hand calculations. We can estimate the joint reaction forces using the softwares and simulation. So this is the inverse dynamics method, like the link segment model. So in inverse dynamics method, we represent each bone using some link. So like you can see, this is the anatomical model. Here the femur is represented using this link 1, 2, then tibia is represented using the link 2, 3, and the foot is represented using the link 3, 4. So now you can use these links, uh, we can separate these links, and like we have separated this foot from the ankle joint. So now from in the foot, if there is ground reaction force here acting, then using this particular segment, we can calculate the joint reaction forces at the ankle, Rx3 and Ry3, and also the moment around the ankle joint. So in the next step, we can use those data for finding the joint reaction forces in our knee joint. So means inverse, we can do the inverse approach. Like first, we'll take this foot model, then we'll estimate the reaction forces and moment at the ankle joint. Then for the next step, we'll use this the tibia bone, and using the reaction forces in the ankle joint, we'll estimate the reaction forces in the knee joint. And in the next step, these reaction forces in the knee joint will be used to calculate the reaction forces in the hip joint. So like means like this, we can estimate the joint reaction. We can calculate the joint reaction forces for any joint which we want. So there is one simple problem which I will now solve. So here in this figure, you have seen like there are three links. So I have taken the link, means the foot link, which is a 3, 4. So detailed problem is given here. So the problem says that during the toe phase of the gait cycle, the ground reaction forces Rx and Ry acting on the foot are found to be 90.8 and 612.1 Newton. Now we need to calculate the joint reaction force and net muscle moment at the ankle. So where is the ankle? Ankle joint is here. So we need to estimate the joint reaction force at the ankle. So I will draw two components of joint reaction forces. That will be Rxa and Rya, and also the muscle moment. Muscle moment M. Okay, the mass is given and the mass of the foot is given 0.9 kg. So how to solve this problem? So if you have solved, if you have seen my previous lectures, there I have told about the force equilibrium and moment equilibrium, which we can use for solving any problem in the biomechanics. So here we'll use those equilibrium equations. So we have two equations which are summation fx is 0 and summation fy is 0. That means sum of the forces in the x direction is 0 if there is no net acceleration acting on the body, and sum of the forces in the y direction is 0. So if we use this first equation, summation fx 0, so here what are the forces that are acting in the x direction? So it is rx plus rxa equal to 0, because there are no other forces which are acting in the x direction. So from here, rxa equal to minus rx. And what is rx? Rx is given 90.8. So it is minus 90.8 Newton. Now, if we use the second equation, it is summation fy is 0. And the forces that are acting in the y direction are ry plus rya, and weight of the foot w, which is acting in the negative y direction. So it is 0. So ry is given 612.1 plus rya minus, and w, we need to find out the w. Mass of the foot is given 0.9. So we need to multiply 0.9 with 9.8 equal to 0. So if we solve this, then it will come minus 603.28. So we have found out the reaction forces at the ankle joint. And why we are getting the answer is minus because previously we have assumed that the reaction force direction will be like this, like in the positive x and positive y direction, but we have found out that the direction should be opposite. So the actual direction will be so this should be the actual direction in the negative x direction and the negative y direction. Okay, we have found out the joint reaction forces. Next, we need to find out the net muscle moment at the ankle. So we'll take the moment. We'll again use the moment equilibrium equation, and we'll take moments about the ankle joint. So let it be A, ankle joint. So we'll write moment about the ankle joint is 0. And here we'll take anti-clockwise direction positive. So the muscle moment, we are assuming that it will act in the anti-clockwise direction, which is given by m. So it will come as m. And what will be the other moments? One moment will be because of w, and it will be in the clockwise direction, so it will be negative minus w dot. The moment term is given 3 centimeters, so we'll take 0.03, and one moment will be because of rx, and it will be in the counterclockwise direction, so it will be positive. and the moment term is 0.15 plus Rx dot 0.15, and Ry also produce moment in the counterclockwise direction, so it will be again positive plus Ry dot, this distance is given 9 centimeter, 0.09 equal to 0. Okay, now we'll substitute the values here. M minus, what is W? W is mass of the food is 0.9, 9.8, and 0.03 plus Rx. Rx is given 90.8 plus 90.8, 0.15 plus Ry is 612.1, 0.09. So from here we'll get M equal to we'll get M equal to minus 68.4 Newton meter. So again we are getting minus, that means the moment will not act in the counterclockwise direction, so it will act in the clockwise direction. So the moment will act in the clockwise direction. So the directions which are showing using the black colors, those are the actual directions for the joint reaction forces and the net muscle moment at the ankle joint. Okay. So this is the answer. There is one more problem. Similar to my previous problem, but here accelerations are given. In the previous problem, there was no acceleration, but here acceleration like the translational acceleration and the rotational accelerations are given. So here we need to use the equations of motion. That means the Newton's second law of motion. So this is the foot. The triangle shaped object is foot, representing a foot, and this A is an ankle, A is the ankle joint. So here first we'll calculate we'll need these distances from the ankle joint to this center of gravity of the foot. This distance we'll need, and this distance also we'll need, and this vertical distance also we'll need for calculating the moment. So first we'll calculate these distances, because here the distances are not given directly and the coordinates are given. So here this distance is 5.6. 5.6, it is in centimeter. And this is 13.5 centimeter. And the vertical distance This is 15.1 centimeter. So in the previous problem, we used that we used the summation fx equal to 0. But here, since there is acceleration, so we'll use summation fx mass into acceleration in the x direction. And one more equation is summation fy equal to mass into acceleration in y direction. And there is summation moment about the ankle joint is I multiplied by angular acceleration alpha. Okay. In my previous equation, because there was no accelerations given, so we used summation fx 0. Means we put acceleration term 0, then that simplified equation we have used. But here we need to use the accelerations also because these values are given. So if we use this summation fx equal to mass into acceleration in x direction, what we will get using this? We need to find out the net forces, total forces acting in the x direction. So one force is given, this fx 160.25 Newton, and we need to find out this fax and fay. So in the x direction at the ankle joint there is fax plus 160.25 equal to now mass is given 1.12 and acceleration is 3.25. So if we use this, fx will come minus 156.6 Newton. Okay, that means here the direction is given in the positive x direction, the direction will be opposite. And so we have found out the fx. Now we'll use the second equation, which is summation fy equal to mass into acceleration in y direction. So it is summation fy. If we use this, what are the forces acting in y direction? One force is 765.96. And weight of the foot is acting in the vertically downward direction. So it will be minus 1.12 into 9.8. And this fay is acting in the upward direction plus fay. There are no other forces and it will be equal to mass is 1.12, acceleration in y direction is 1.78. So solving this, we'll get fay equal to we'll get fay is minus 752.9 Newton. So we have got that fay will also act in the vertically downward direction. So now we have found the joint reaction forces at the ankle joint. Now we'll find the muscle moments, MA. So for calculating the muscle moment, we need to use this equation, summation of moment about the ankle joint is equal to I multiplied by the angular acceleration. So we'll write about the ankle joint is I into the angular acceleration. So what is the moment about the ankle joint? So we'll assume that this anti-clockwise is positive. So this MA is acting in the anti-clockwise direction. So it is MA, and this 1.12 kg, it is producing moment in the clockwise direction, and it is at a distance of 5.6 centimeter. So it is minus 1.12. We need to convert into Newton. 1.10 into 9.8 into 5.6. We'll write in centimeter, sorry, meter. And this Fy is acting in the counterclockwise direction, so it will be positive, plus 765.96 multiplied by this distance is 13.5. It will be 0.135, and this 160.25, it is acting in the counterclockwise direction, so it will also be positive, plus 160.25, and this moment term is 15.1, so it is 0.151 equal to I into alpha. I is given 0.01 and alpha is minus 45.35. 0.01 into minus 45.35. So if we solve this, then we'll get MA equal to we'll get MA is minus 127.4 Newton meter. So we have got all the joint reaction force and the muscle moment negative. So the actual directions will be opposite to what it was given in the question. So FAX will act in the negative x direction, and FAY will act in the negative y direction, and MA will act in the clockwise direction. So this will be the actual directions for the muscle moments and the joint reaction forces. So is it understood? If you do you have any question, any doubt?
No, sir.
Okay. Okay, so that was all for today. So thank you for attending the class. So like today, I will means these classes will be continued up means up to the last week 8. So I will take the classes on every Friday till the end of this course. So you can attend these classes means for getting an idea how to solve numerical problems, and also I will teach you some concepts also, and I will solve some problems using those concepts. So it will be helpful for you if you attend if you attend the examination for getting the certificate. Means the final examination at the end of the course. So it will be helpful for you. So if you have any queries, you can mail me in my mail ID. And yeah, thank you. You will meet in the next class. If you have any question, you can ask.
Thank you, sir.
Thank you. Okay, I will end the class now.